It doesn't bother me. It's as long as there's some people in here, I'm happy. If I had to teach to a screen, that would be miserable. Oh my gosh. I enjoy getting to interact with you all and all that stuff. All right, I sent you all a tool yesterday. I sent you all that Excel spreadsheet thing. I'm going to go ahead and open it up, walk you all through it. Use it or don't, the choice is up to you, but I just want to make sure you all, if you want to use it, you can use it. All right, I'm going to use the example document. So I sent you all, I technically sent it to you all as a Google Sheets link, but that was just to make it easier for me. Download it as an Excel spreadsheet if you want. But I'm going to go ahead and Yo.
Your microphone
is it not good?
No, it's like super rumbly.
This is rumbly?
Yeah.
New mic.
Just saying.
No, I appreciate that. Is that? Huh? All right, I'll just keep yelling until it works. Is that better? Oh, thanks. Okay, so here's what the... Ooh, that's so loud now. Here's what the document looks like. So, if you remember from the syllabus, there's various grade categories. So I'm just going to zoom in kind of up here up top. You have the labs, which are worth 15% of your grade. You have the top hat, which is worth 10% of your grade. Quizzes worth 25%. Test 1 is 15%. Test 2 is 15%. And the final is worth 20%. So each of those are percentage. And if you all go to web courses, there should be a column somewhere in your grades that says, here's how much percentage of lab points you have. Here's how much percentage of top hat you have. Here's how much percentage of quizzes you have. And so if you want to use this, so the reason this exists is because web courses does have things that let you plug in numbers and see how it affects your grade, but it doesn't have a couple things built into it, and there's no way for me to build these in. Grading policies I'm using specifically, your final will replace your lowest test grade if it's better than your lowest test grade. That's something I can't build into Canvas. I have to do that manually. It's not a big deal, but you can't check that out in Canvas. And the other is I'm going to give you the grade in the class. I'm going to check your grade with top hat and your grade without top hat, and whichever is higher, that's what I'm going to keep, because attendance is kind of up to you kind of thing, but I incentivize it. The downside of not doing top hat is that everything else then becomes worth more points. So the tests become worth more points, the quizzes more points. Everything fills the void that was top hat, whatever. So let's just play around with this. I'm just going to show you all how it works, and then if you want to use it, great. If not, great. So say you get a 90% on your labs. You put a 90 into that, and then that goes away. Let's say you've been getting 95% on the top hat. Let's say you've got 90% on the quizzes. Let's say test 1, you got we'll do the average. 66%. And test 2 hasn't happened, so we leave it blank. So this is showing your current grade now. This current grade does not include test. This current grade is the current grade. It's actually, okay, so it's taking this midterm overall, so this looks crappy, so you actually do need to put your test 2 total. Basically, if you want this number to be something reasonable, you got to make up a number for test 2. What number are we going to make up for test 2? I don't care. Let's say 70 it is. Great. And then this, if you got a 70, this would be your grade with top hat. This would be your grade without top hat. Takes the higher of the two, yang. Great. Now, if you look down here, the final grade in the course sucks because we haven't done the final yet. So the final, so this is like your current grade, assuming you do test 2 and you get a 75. Then down here, if you want to see your final grade, you got to make up a score for the final. I don't care. We're going to pick a number. It doesn't really matter. Let's say you score a 72. And boom, it spits out what grade you're going to get in the class. And then down here, what you can check is, so remember we said the final was a 72. notice that test 1, which was the lowest grade, got replaced with the 72. So it lets you see that happened. It's kind of a check. That's for me and for you all to check it. And, there's the final over there as well as the 72. So don't fiddle with anything. Don't edit any of these values. These are all referencing things. They're all little equations that are referencing other stuff. But this is the stuff, anything that was red, that's where you change stuff. And then, it spits it out and you're like, man, I want to see what I need to get an A. You can just play around with the numbers until it gets to an A. Yeah, good. That's the goal. I made this in previous semesters, so I just tend to have to update it per class, and it's not a big deal. But there you go. You all wonder why we're learning Excel stuff? Like, this is all built on Excel equations, and you can look through it if you're curious how it does it. It's all there. It's nothing too complicated.
You don't do pluses, right?
No, I do not do pluses, and I'll also be fully transparent with you all, because if you look through this, you'll realize it. Notice I tell you all the letter grade here. If you go in here, you can see how that's calculated. And so what I'm going to straight up tell you all now is I round up is the way it works. So that's always people ask, oh, do you round or stuff like that? I round up. So if you have a 90 or above is an A, an 80 or above is a B. If you have an 89.01, that will round up to a 90. Okay, so it rounds up. Now, if you have an 89 flat, which is like I don't know how that would happen, it's going to stay at 89. If you have a 79.9, it'll round up to an 89, and 89 is a B. So just know, if you're wondering at the end, how does he do rounding? I just round up. 90 or above A, 80 or above B, 70 or above, and you can actually see that in this logic. But.
And then there's also that quiz that we took in the beginning.
Oh, goodness. Yes, that will be Sorry, that is not included here. Just chuck an extra point on here.
Okay.
I forgot about that one. So that one, if you all did do the extra credit thing, just take whatever number is here and add 1.
Okay.
Or I think I have to remember. Each one's worth, I think, 0.5%. There'll be one at the end. If you do that one, then I think so. I have to double check. Whatever I said in my announcement, did I say 0.5% or? It was 1%? All right, I have to double check. Yeah, it's actually, whatever I put in writing is the amount that you get. So you can just check my announcement on that. I won't say anything now because I don't remember. No one will be confused. And so you said this. If I said in my announcement it was 1% for doing the pre-test and 1% for doing the post-test, then add.
I think it was half and half. That's why
Okay. That's if you do the pre and the post, add 1 to this, and there you go. So this exists again. The link I sent you all is to the Google Sheets version of this. If you don't want to make a Google account, just email me and I can email you the Excel file for this. Or alternatively, if you all open the announcement, you can go to this one and then download this one without an account, whatever. I leave it in your capable hands. But yeah, done. All right. Peter's got a joke. No, he doesn't. Sophia's got a joke.
Which one was the one that wasn't working?
That one, I think.
Okay. So, teachers with lazy eyes are the worst. They can't control their pupils.
Their eyeballs. Their pupils. Yeah.
Let's just say your final is lower than 2 of them. It's just like 3 methods.
Yeah, if your final is lower than one of your test grades, it'll still be your final grade. But the finals were 20% instead of 15%.
Oh, okay.
It's very close to the same percent, but because it's longer and all that jazz. And I can also tell you all the final will probably be like 40 multiple choice. There won't be any free response. The reason there won't be any free response is because I have like 4 days to get grading done or something silly like that. And I also, the way I do grading is I get it done and then I want to give you all like a day or two to like look it over and double check my work. I'm going to double check my own work, but it's good to give you all a chance to also look over everything and make sure it's all good and whatever. So I give you all like a day or two to, hey, look at everything's in, look it over. Does it all look correct? Notify me if there's anything that's missing or whatever. And yeah, so it'll be 2 hours. The final will be 2 hours and 50 minutes in this room. The time will be, I think, 7:30, or 7 o'clock. I don't remember. Yeah. That's, you can look that one up. It's on there, but it'll be probably 40 multiple choice, 2 hours 50 minutes. It's cumulative, which I know stinks, but the idea of the test is that it should represent, like, by the end of my course, you should know all the things I taught, so the test should represent that, and that's the idea. It'll be 2/3, it'll be like 65 to 70% stuff from test 1, test 2, and then like 30% new stuff that we covered after test 2.
Would you recommend like practicing with the past exams?
Yeah, that's useful. Yeah. Any previous problems I've done is good practice. Past exams, past quizzes, past problems, like all of it is useful. Okay. All right. So, last class, we talked about momentum, and it was a super easy equation: m times v. It's great. And the hand wavy definition is how hard it is to solve something. You're not going to find that in any scientific textbook, but it's a good sense of what it is. Momentum is great because momentum is conserved. So which is a fancy thing that physicists always say about lots of things. And it means that what you start with is what you end with. So if we scroll, assuming there's no extra forces acting on it, no external forces, no one's pushing it, gravity's not affecting it. As long as there's nothing outside the objects you're caring about that are affecting each other, as far as forces are concerned, what you start with momentum is what you end with momentum. Momentum is one of those things that in physics, at some point they just kind of stop working with velocity and they just start using momentum instead. Because it's a conserved quantity, it's kind of a funky thing. At some point, physicists stop. We just switch to momentum entirely. They have strong feelings about momentum. So like if you all remember, the equation for kinetic energy is 1/2 mv squared. That is also equal to p squared over 2m. You don't need to know. You can kind of see that for yourself if you want to. Remember, p is mv squared. These two things are identical if you just go through the algebra. Physicists love momentum. They use momentum for so many things. They even work in something called momentum space, which I don't exactly know what that is, but they love it. Momentum's great because it's a conserved quantity. Super, super, super useful. You all don't need to bother with any of that. You don't need to know necessarily all that, but I'm just trying to tell you all it's important. People love it. So today, and then let me show you all. There's different types of collisions. You could have multiple objects bouncing off each other, or you could have multiple objects coming together and getting stuck, or you can have objects that start together and like separate, split up. And so all we're going to do today is solve some of these problems. That's pretty much the name of the game. So yeah, last time we did this. Great, I'll chuck this equation. So last class we did this question. We're going to do a couple more and then we'll start jumping into actually solving problems. So I had 2 objects, each with their own momentum. What was their total momentum? We just found the momentum of each and added them together. Great. All right, if I have 2 objects, M1 and M2, and they get stuck together, what is their new mass? Yeah, don't overthink it. This is not a trick. This is not a trick question. In general, I do my problems with this question.
Right? That was true.
In general. I know some feel like they are.
If you look closely, you'll see
Like, what's the acceleration at the highest point? The fly in the truck, yeah. It feels trick, but it's just changing your viewpoint about force. All right, I'm gonna give y'all like 20 more seconds. Like, don't overthink this. I'm optimistic everyone will get this right. Let's see. All right, and 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Foul. All right, this is going to be crazy if you have an object and you have another object and then they get stuck together. If this one is 1 kilogram and this one's 2 kilograms, how much is the one together? 3 kilograms. Yeah, you just add them together. You know. Yay! Great. Why is this relevant? Don't worry. It's all going to come together. If I have two objects, M1 and M2, with velocities V1 and V2, they hit each other and get stuck together and end with a velocity of V3, what's the equation for conservation of momentum? It's putting the pieces together. You all found the beginning, two objects separated. You all found this little piece. So it's building, add up your momentums that you start with, and that's going to equal the momentums that you end with. That's what we're practicing. We're practicing doing conservation momentum, building the equations.
I think you mentioned C because of momentum. Conservatively, there's no massive event to get stuff together. So not I'm
It should be, yes. Thanks. And I actually need to give the right answer for this, so I don't have to go back and. Yay! Oh, we almost did it.
You just got it. Because I think you want to count.
This is great.
No, I actually don't have. I only have Christmas. I have several Christmas ones. We'll combine them. The problem with Christmas ones is you can only wear. At some point, I will wear them, but it's a weird thing. Then it's like. Then you get a million questions. It's not Christmas. What are you wearing a Christmas one? Yeah, that's literally the reason. It's just existing in my closet. Yeah. No, I don't have any other holidays. I have 4th of July.
Oh wait, yeah, you're right. Because it would be both the masses.
Oh yeah, no, I don't want to. You could get a turkey one. Turkey's great. What do y'all pick? Snowcone.
I should have let you know. No, dude, how did there you go.
And then this side, why is there Boston the same? You're in a car going 60 miles per hour, everything with the car. Okay. All right, 10 more seconds, which is overkill. In 5, 4, 3, 2, 1. Boop. All right, so you got two objects. They're zooming. Now, which way? We're assuming these are going all horizontally or all vertically. So great, you got this guy going this way. You got this other one going this way. They don't have to be going towards each other. They just have to be able to collide. So notice in this picture, I drew the first one going faster than the second one. How do you know it's faster? Y'all tell me. How can you tell from the picture it's faster? The bigger arrow. These arrows correspond to the velocities. So yeah, remember the size of the arrows matters. Great. If they collide with each other, which way are they going to move at the end? Right, left, up, down? To the right. You know, it's what you expect. That's our V3. So yeah, this is how we build this. We have the momentum plus the momentum of object 2 equals the momentum of both objects together, which is their total mass times their velocity. Now, if you answered D, that's also correct because it's the exact same thing. C and D are the exact same thing. D is just written there to show you that generally we'll write it as C because it shows it that they're together. But D, we just brought the V3 to both terms to show, hey, they have the same velocity. Why do they have the same velocity? They're stuck together. If you're stuck together, you're going the same speed. Like, if you're not, then you're not going to be stuck together by definition. Great. Both of those are good. Good job, squad. All right. So yeah, if you have multiple objects stuck together, add up their masses, multiply by velocity, great. Just like you want it to be. Okay. This next slide I'm about to show you is going to have a few equations on it. You do not need to, in fact, I don't even want you necessarily to write down these equations. You can if you want to. The next slide is a bunch of examples. It's not new equations. It's examples of various scenarios. And this is not going to cover all the scenarios you're going to run into. So this is just to show you examples. If you have two objects that bounce off each other, elastic means they bounce off each other. We have M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. All of these. So momentum. This slide, if it didn't exist, you shouldn't be negatively affected. You are going to build the momentum equations for every single problem. These are just examples to give you a sense of what they might look like. But if I have 3 objects, you can't use any of these. If I have 4 objects, you can't use any of these. So these are just examples to give you a sense of what they might look like. If you have 2 objects and they run into each other or whatever, and then they bounce off each other, great, that's the first one. If you have 2 objects that collide and they get stuck, that's the one that you all just did the second one. You built the second one yourself already. You are capable of doing this. And then the last one is 2 objects that started together and they separated. And then the last thing's really important. In momentum problems, they're vectors, so we have to do this twice. So like I wrote that equation up top. Sum of momentum's initial equals sum of momentum's final. You need to do sum of momentum's initial in the x equals sum of momentum's final in the x. And you have to do sum of momentum's initial in the y equals sum of momentum's final in the y. There is no shortcuts. There is no getting around this. I don't make the rules of the universe. I just teach them. So again, if ever you're like, ugh, vectors, why do we have to do this? Because that's how the world works. It's just, sorry. Get angry at however you believe the world is being maintained. If you think there's someone in charge of maintaining the world, yell at them. If you don't, yeah, I don't know who to yell at. Yell at the wind or something. Yeah. So, anywho, they're the rules of the universe. We just follow them. Okay, so again, the goal of this slide, you should not reference this slide to solve problems. This slide is not a reference for what equation to use. You will not see these equations on the formula sheet. The equation that you're going to see on the formula sheet is sum of momentum's initial equals sum of momentum's final. It's like the energy you start with is the energy you end with, that kind of idea. You have to build it. You have to build the equation, and that's all we're going to do for the next, the rest of today is just practice building it. Just do a bunch of problems with it. So, give you all some tips, and then we're going to do it. It's going to be a good time. All right. If there's a collision or a separation, I'm going to add that. If there's a collision or separation, meaning, they split up, you're going to use conservation of momentum, like guaranteed. 2 objects hit each other, bounce off. 2 objects start together, and they separate. You're going to draw a picture. That's going to help you keep track of the objects and which way they're going and how many of them there are and whether they're together or separate or all that. We're going to identify what type of collision. Do they bounce off each other? Do they get stuck together? Or do they start together and separate? Those are the 3 scenarios. There's no other scenarios. Either they bounce off, stick together, or they started together and separated. And then, you do the rest of normal things. Givens, missing, equation, solve, split everything into x and y. It's a good time. right. So here's our first one. Two-figure skater. And actually, before I do this, let me open the problem set and make sure that this number, it says it's linear momentum number 7. It might have shifted around. Oh, that's great. Scroll. Ah, great. It still is linear momentum number 7. And then I also want to check whether, okay, you all are, nope, it's still there. All right, the boy in the boulder. Ugh, we're not going to probably worry about that one too much, but. All right, two-figure skaters are coasting in the same direction, meaning, you tell me, what does coasting mean? If you're coasting in your car,
You're not changing velocity.
you're not getting faster and you're not getting slower. Cruise control. They're going at a constant velocity. Every momentum problem, they're going to be at a constant velocity. Yes, they'll collide and then we'll change it. You're never going to have a momentum problem where they're accelerating because that would be awful. It wouldn't be the worst. You would just have to find their velocity the instant before their collision, which wouldn't be the worst thing in the world. But anyway, two-figure skaters are coasting in the same direction. Leading skater moving at 5.5, trailing skater moving at 6.2. When the trailing skater catches up to the leading skater, he picks her up without applying any horizontal force. That's just saying the momentum's conserved. If the trailing skater is 50% heavier, or we should rephrase this, has 50% more mass, in this case it's the same thing, than the 50-kilogram leading skater, what is their speed after he picks her up? Draw a picture. Like, if it seems like there's a lot going on here, there is. It's like a whole paragraph. Draw a picture.
I don't know what the problem solving part is. Every time I read them, they're so confusing.
It's a lot. The reason...
Problem set ones, they're always like just huge and like...
Yeah. The reason I have them is it's more actually accurate to the real world in that the real world has a lot of things going on.
Yeah.
They're on a test. I keep it shorter for the sake of time, and I just want to do the physics, but like the real world's messy.
Yeah, it makes it like my brain think more.
Yeah, no, but I get it. It's not. You do have to think a lot harder, and you have to think, what is going on? There's so much, but it's just more of a. If someone tells you something's happening in the real world, they're going to tell you a bunch of stuff.
Yeah.
But it does. Don't worry, I'm with you on that. It's okay. It's a lot. I'm just writing down. And in your picture, you should have a beginning and an end, an initial and a final. Before they collide and then after they collide.
What? I'm going to do something
I love that you have them hold them up too. Mine are just going to be blobs, so I appreciate the effort you put in. Oh, yeah, no, that's great. That's great. I love it. I'm here for it.
Yeah. That'd be sad. It's good.
Oh, right.
I don't know. I'm tired.
So they're all set together. Cool. Yeah. So, how we have two people colliding. So what do we use to solve this? What? Yeah, we're gonna build it though. So sum of momentum I start with equals sum of momentum. What's the equation for momentum?
Yes.
Two variables. No.
Yeah.
Do you know the mass of person
Yeah, we're
one?
getting the stats
So
here
you
too.
just do M1.
Do you know the mass of person two?
Makes sense.
What is it?
That gives you a big number and then divide by.
So the mass, you gotta make sure you pick the right person.
Yeah.
Oh, it's not.
Yeah, so
Both of the masses added together.
the
think
leading
that just comes
skater
out.
is 50 kilograms. What's the mass of the?
Because you wanna,
740 divided by total mass of 75.
There you go. How did you do that?
that just comes down. I didn't realize that, so I wrote it down. I just did it for a while.
All right, so
Alright.
we draw a pretty picture. Here's figure skater 1, here's figure skater 2, and all their blobby goodness. The main thing in this problem you gotta be careful of is just making sure you know who's who. The leading skater is going slower, so we'll call that, we're gonna call this person 2 and this person 1. So V2 initial is gonna be 5.5 meters per second. And then this person is going faster. This is V1 initial equals 6.2 meters per second. So already I'm using my notation here. It's not the worst thing if you don't use your notation here, but you will at some point need to do that. I have the velocity of person 1 in the beginning. I have the velocity of person 2 in the beginning. And by putting all that there, it just makes it easier later on. Great. What happens at the end? Do they bounce off each other, stick together, or some secret option? Yeah, they're stuck together. Great. Do we know how fast they're going?
No.
No. We'll just call this V final. We don't need to clarify 1, 2, 3 because there's just one blob at the end. So we don't need to eliminate 1 and 2. Okay. What's the mass of person 1?
75
So how did you all get that? I heard 75.
divided 50 by 2 and then added it to 50.
So it says, yeah, the training skater is 50% heavier. That means if you're 50% heavier, you are going to have 50% more mass. Those are directly correlated. Everyone's on the same planet here. So I know I said heavier, but in this context, if you're 50% heavier, you also have 50% more mass because we're both on Earth. So, yay. Great. And, we got a big old list of givens now. They're kind of chucked in here, so whatever. I'm not going to rewrite them. What are we solving for?
The velocity part.
We have a collision. What equation are we going to use? Momentum. Sum of momentum we start with equals sum of momentum we end with. Now, we don't want to forget that this is a vector and we got x and y components. In this picture, are they going up and down at all?
No.
No. Are they going left and right? Yeah, so I'm just going to write both of them here just to remind us that this is a thing. So I'm just writing both of them, that the y direction and the x direction. And then I'm going to cross out the y1 because there is no y components here. So I'm just writing it out just as an exercise of don't forget that this is a thing. I'm going to give you all a problem. Here, let me just show you all. In a few slides, we're going to do this problem.
No, we skipped it.
It's not the worst thing in the world. It's just there's x and y components. Great. Okay, now you all got to build this equation. Pro tip, you already built this equation. You already done this. It was our clicker question. I have two objects which are separated and then run into each other. Make the conservation momentum equation for it. And then plug in your numbers, solve, and have a great time. Oh, and the answer's up there. So. And if you all feel like you understand what's going on here, great. It's more the same moving forward.
Great, so we're done.
Yeah. Well, it gets worse because you have x and y.
Why are you doing it twice?
And there is an elastic collision where I'm just going to show you that it's gross. And then give you kind of a little shortcut, but not going to make you do the algebra.
Ooh.
An elastic collision, you have if you don't know that, I can give you a problem that's an elastic collision. And then I have the two objects, and I can just give you the initial velocities. And then you have two unknowns. The unknown for the final for person one, person two. So you need two equations. Momentum will be one of the equations. Energy will be the other equation. And No, well, the math is very unpleasant. I mean, it's
Don't be doing the ones where you don't give us half the variables we should have as well.
no, I never do that. You always have.
You don't need math.
Well, that's great.
Those out.
Yeah. You love that.
Oh, that's not right.
You love to see that. But it's so cool. It means everything on an inclined plane, the mass doesn't matter. In the real world, it probably does actually have some effect. But
Exactly.
mostly, 90% it doesn't matter.
That's just
Yeah. It's good. We love that.
Oh, sorry, I already solved it. I got the final way. Sorry, so I took the moving and then the mass of the traveler, mass of the leader, all of that.
All right, so we just build it. If you build it, then you can solve it. M1 V1 initial plus M2 V2 initial.
No, I get it. I was like,
Yay! It's the one that we did in our clicker or our top hat. Yeah. No, you got to build them. You got to build them. So that's where. Do not look at this list of equations to like. How did I make this equation? I didn't memorize this. I didn't get that equation by going back to the slide and doing this. That's not how you want to solve these. I give this slide as an example. Do not fall in the bad habit of using this examples as what equation to use. I'm going to give you problems where you have multiple objects and you can't. This is just examples. So how did I build this? I looked at my equation and said, all right, you all tell me, how many objects do I start with? 2. So momentum of object 1 initial plus momentum of object 2 initial. Great. 2 objects. They're separated. How many objects do I have at the end? 1 equals the final momentum. There's only 1 object, so I just put 1 object there. And then what's the equation for momentum? M times V. So M1 V1 initial, that is P1. M2 V2 initial, that is P2. Equals the total mass, because they're stuck together, times V final. You build it. And it's just add up all your momentums to begin with, equals all your momentums that you end with. M times V's plus M times V's plus M times V's plus, however many objects you have. If I had 10 objects, do I want to do that? You know what? Let's practice this. This is good. I'm not going to make it a top hat question because, oh my gosh, it'd be so much typing for me. I'm going to give you all something wild that I'm never going to give you a problem on, just to see if you can do it. Object 1, 2, and 3 are all moving towards each other. They all collide, and object 1 and 2 get stuck together, while object 3 bounces off. Make the conservation of momentum equation. Draw a picture of this. You will not find this one in that list. Nor will I necessarily give you all one like this because it's got a combination of things happening. But it's practice for can you build the equation. Draw a picture of it. Add up your P's. Bro, there you go. Now you know how to, you can do this. You can basically build a conservation of it. Right? That's the new thing. Any other skill you need a problem with, like breaking vectors into X and Y and stuff like that.
just wasn't sure if we kept the same velocity
That's a good question. So,
yeah,
yeah, you can call these kind of whatever you want. These ones are going to have the same velocity. This guy's going to have a different velocity. Because everything we imagine that now, if it was traveling to the right, now
M1
it's traveling
plus
to the left.
M2
And because these are vectors, we'll have positive and negatives.
velocity final plus M3
Yep.
times
Yep.
V1.
That'll do.
Yeah, I want this to tell you it's right.
Nice. Just lost the plus sign somewhere. No, perfect. That's literally it. That's it. That's concentration.
Let's see if it's right.
I'm very happy to see these are going really well.
M1 plus V1. Or M1.
So you all the like individual ones, and then this goes
Yep.
through that combined, and then that's
Yep.
that.
Perfect.
Okay, awesome.
The only thing is this will not be the same as this.
Nobody.
Who knows? It's call it V, call it whatever you want.
So then instead of this, it would just be like
So it's still M3
V3F.
times
is
N.
equal to
Times N.
M1 plus
Yeah, I just saw. I think you just had
Yes,
3.
I did.
Yeah.
Okay.
It's gonna bounce off because
plus M3.
it can even come in like this and then bounce off this way or bounce off this.
Got you.
Yeah.
It's a different one.
It's definitely a different one. It's
I'm not sure that's
technically
entirely-
possible for it to be the same, but it'd have to be a pretty like
It's just the elastic equation.
very, very, very. That's very, very unlikely.
Mm.
All right, I'm very, very pleased to see this. That you all have these skills. So yeah, you got object 1 coming in hot. Look, I'm gonna even be kind, and I'm gonna make it all just in the x direction. Otherwise, it'd be vectors and let. Object 1, object 2, object 3. That's the beginning, and then at the end, great. There's object 1 and object 2. They're stuck together, and object 3 is zooming its way over here. So yeah, we're conservation momentum. Sum of momentum's initial equals sum of momentum's final. How many objects do I have in the beginning? 3. So we're going to do M1 times V1 initial plus M2 times V2 initial plus M3 times V3 initial equals, how many objects do I have at the end?
3.
Wow.
Kinda.
Kinda, sorta. How many, like, we're going to say 2 objects, just like, we're going to have 2 momentums. Maybe that's a better way of phrasing that. M1 and M2 are stuck together. So we'll call that 1, 2 final, whatever. You can call it whatever you want. You all had, I saw like people put V4, that's fine, as long as you know what it is. The notation I used here, I have object 1 and 2 stuck together and it's final, so great. And then I have M3, V3 final. What you can use whatever notation you want as long as you understand what it means. The notation I use here, if anyone read this, they'd be able to parse it out, hopefully. Velocity 1, let me rephrase that, like, it has the information without the picture. V1 initial, V2 initial, V3 initial, the 3's go together, the 2's go together, the 1's go together. Here I have 1, 2 final, because it's the velocity of them together, and 3 final, yay. Great. Fantastic. Do we want to do the boy and the boulder? I don't want to, okay, we're not going to do that one yet, because I want to keep you all confident and not sad. The boy and the boulder one is mathy.
I'm going to say, I want you to do this.
We will do the boy and the boulder. It's going to happen. If nothing else, so I can show you all that it exists. And then I'll tell you I'm not going to give you one like it on the exam.
Okay.
Yeah. All right. Great. I'm going to make this picture much bigger. A 0.9 kilogram falcon is diving at 28 meters per second at a downward angle of 35 degrees. It catches a 0.325 kilogram pigeon from behind in midair. They hug and they're stuck together. What's their combined velocity after impact? If the pigeon's initial velocity was 7 meters per second directed horizontally. You need to make 2 equations. If you are making 1 equation, you're doing something wrong.
Oh, and like.
Is the solution missing a J?
Yeah, it is. Boop. And I know there's a picture up here. Make sure you redraw the picture on your own paper. Otherwise, you're going to be acting like a snapping your head back and forth, working constantly. That's a pain. Save your neck muscles.
Alright,
For these types of problems.
cosine 35 times 20 equals something else in that direction.
For these types of problems, do I have to use derivative?
Yes. You have to split it into X and Y.
Oh, wait.
Like not splitting into X and Y was the most common mistake on the exam.
Yeah, people don't like it.
Wait.
And the reason it matters is if we don't split it X and Y, then you're saying it doesn't matter which way the falcon hits it, but it does. I love that you write your own mouse pad. No, it's good. No, I guess it.
I love the mouse pad.
Yeah. I get that. Fried smooth. No, that brings me back to making my own mouse pad. Many years ago. Huh? No, oh no, I never actually made one. But no, just like buying the custom one. Oh, okay. That brings me back. Well, someone did this. I said someone did that video.
Yeah.
That's pretty old. Yeah. That's right.
M1N and
Now, if you want to be, so something that is always fun as you get older. I graduated high school in 2011.
2 of the M times like 2 minutes.
Which is what age? Yes. It's one of those. You can do the math. I'm 31 now. Okay. Yeah. No, it's one of those interesting things. Time, 10 years is a lot more than people it seems like.
Yeah.
It's one of those weird things.
Is the Falcon 2 momentum?
Depends what you mean by that.
Okay, so I obviously for the Falcon, I found the momentum.
Yeah, the X and the Y, good.
But
Is it
now
positive or negative? Yeah, you gotta be
in
super
the
careful.
Y direction, right?
Yeah.
Then the X direction is positive.
Yeah, you have to be super careful about it. That's something I can guarantee.
Okay, awesome.
Have to.
So is the Falcon 2 momentum?
You are going to need to do 2 momentum equations, one for the X
Yes.
and one for the Y.
Okay.
Yep.
I think it's gonna be like M1X, M1Y, and then
All the X's are together. You build one equation with all. Remember, anytime.
Also, mass doesn't have direction.
Yeah, that's true as well. Mass with the 2 mass, there's no X and Y component. But
well, yeah, sorry.
yeah, anytime you use X components, it should only be X components.
So
Anytime you do Y components, it should only be Y components.
for the mass in the X direction, I do combine with the Jerry Hopkins mass. So it's gonna be mass.
You do that regard X or Y. Mass has no X, Y.
Mhm.
Mass will be mass the same as
Yes.
both.
But I mean in terms of like having like let's say sorry,
There you
the M1X plus whatever.
go. N1 V1X plus.
V1.
Sure. Yep. You have 2 objects. So how many objects do you start with?
2.
And then at the end, how many do you have? Yep. That's gonna be true of X and Y.
Oh, okay.
That's gonna be true of X and Y. You just only do the X components in one. You only do the Y components in one.
And then that's the 2 things.
Yeah, yeah.
Oh.
And that'll let you get the X component in one.
That's why I
I think I'll get something.
7 meters per second. Yeah. Yeah. Yep. That's
So
just.
both times are the same because it's like MX and Y.
There is no such thing as an X. Yep. M is in.
M is M, and the M in this equation is both of our figuring
In the final.
in the final.
And only the final. In the initial,
So,
you have 2 objects
yes.
separated from each other.
Mm.
So then you pick their open walks. Here,
But then what's the mass of?
What's the Y component?
What's the Y component?
you tell me, is it up or is there?
Oh, there's no Y component.
So what's the value of it? There you go. Build the equation and plug in the numbers you have.
Okay. I'm lost.
All right. So if you see an arrow and you see an angle, what do you know you're going to have to do?
X and Y.
X and Y. That should just be like a trigger for you all.
Oh my god, I see what I'm doing right now.
Keep you awake late at night, thinking of dreaming of triangles. Now, this is something I just did without, I want to actually make sure you all are doing this. You make a triangle. I highly recommend you make those sides arrows, because if you don't, you're going to probably have forgotten something. I can almost guarantee that at least a third of you all, probably more, I don't want to say made a mistake, but that's kind of, you forgot something. Which way does the arrow point on the bottom? The x component, is it point right or left? So will it be a positive number or a negative number? Positive. What about the arrow and the up down? If you all found the y component and you left it as positive, you were saying that the falcon was going up. And all the math you'll get the wrong answer. If you all made the y component positive, then you're saying that the falcon is hitting the pigeon like that, which does not match our picture and yada, yada, yada. All right, so we'll call the falcon object 1 and the pigeon object 2 because it's easier than writing F and P a bunch of times. Numbers are nice. So this is going to be V1 initial X. This is going to be V2 initial, V1 initial Y. All right, so we write our givens. V1 initial X is going to equal 28 times cosine of 35. What does that equal? 22.14? 94. Great. What about my y component? That's going to be 28, and I'm going to chuck the negative in now. What's the y component? Negative 16.1. If you don't put this negative, you will get the wrong answer, and it'll be very sad. And then, question to you all. Since we're doing this whole x and y component, let's do the pigeons. V2 initial x, V2 initial y. What's my x component of the pigeon's velocity? 7, positive or negative? What's my y component of the pigeon? The pigeon doesn't have any component in the y. It's only going left, right. If you kind of write out this list, it just can help you keep track of it all. Then we got mass 1 and mass 2. We got the mass of the falcon is 0.9 kilograms. Mass 2 is 0.325 kilograms. Okay. Great. What are we solving for? All right. Great. There's all the jazz. So then I copy and paste all this over to here. There's a collision, so we're going to add up our stuff. But remember, you have to do x and y. You have to do x and y. So let's just do x first. How many objects do I start with? 2. How many objects do I end with?
1.
So P1 initial x plus P2 initial x equals, P final x. And then I'm going to write the y equation as well. P initial y equals sum of P final y. How many objects do I start with? 2. How many do I end with? These should both look the same. The only thing that varies is whether you're using x or y components. When you split things into x and y, it doesn't change whether you start with 2 or whether they should look the same. You just put x's in one and you put y's in the other. You just do it twice. It's just like 2D kinematics. You had so much fun doing it once, now you get to do it twice. So, go ahead and build it, do it, see if y'all can get the answers. I'm going to kind of leave it at this spot for now. But I wanted to show you all that the equations look the same in the x and y. 2 objects become 1 object in the x. 2 objects in the y become 1 object in the y. Yeah, darn it. It had a J in the last. Peter fixed that on the last slide. And then this slide had the same typo. Yeah, good catch. Yeah. You don't make it negative to math.
So what I do first, I solve for the velocity and the y-axis before I put in the equation that way. So I have my x equation just times the x velocity and then plus the x velocity
the hypotenuse is always
and this is that. So
because what direction would it be if it was negative?
It's like going down.
Yeah. So the hypotenuse never. You only get positives and negatives when you're in the x or the y. Because it actually
2.325.
a negative.
I'm sorry, I didn't know I was
Which way should it be? That's where we say the angle. So if you wanted to, you could find the angle. And that would actually tell you, yeah. Then you would have to fit size in. Yeah, if you all got this, you can find the hypotenuse. The follow-up to this is what's them together and what's the angle, what's the direction it's going. If you want to just practice that skill, it's useful.
So find overall direction and
magnitude and direction, yeah. 2 favorite phrases that physicists use.
I think I can do that without even looking at anything.
Again, next time you watch Despicable Me, vector. Now you're gonna get the joke.
It's really funny actually.
It's good. Most people have liked it.
But you know how in this house all the tracks that the arrows push you out, right? That's what it is.
What is actually?
I think that's what it is. There's a lot of vector free characters.
There was just a guy. I just remember Despicable Me. There's a guy named his villain name is Vector, and he says he has magnitude and direction.
Oh, that's really fun.
Yeah.
I didn't even think of that.
Yeah, I don't know why he said I don't know what that means functionally, but it's a yeah, basically. See, so now you're a nerd like him. It's good. It's a good place to be.
Yeah.
I mean, if I'm gonna die anyway.
It's inverse and the opposite of adjacent, right?
All right, there's the angle and there's the amount. If you want it.
Yeah, you want to then.
Yeah, but I'm saying like.
Yes, you could do that. There's no.
Yeah, but I'm saying like subtracting the.
So wait,
yeah, like velocity. Would that not be accurate? By the velocity.
I would specify. I'd either say in vector rotation or
So there's not actually a difference
no
between
direction.
this amount and the x.
Yeah. Yeah, this one I put the vector notation just to make it one less.
It's the same thing, right?
Oh, okay, that's fine. But if I
It's
were,
like how
but like if I were to.
Yeah, I would specify.
Like if I did it.
And I put it here just to make
that
it
would be the right
easier for people to
answer.
check their work. If I just put the magnitude
Right,
in,
so-
and that's fine. That's good. That's a skill people should do.
Nice. I think it's
Velocity and x are equal.
Um,
And velocity.
they are an easy thing to yes. I do enjoy
Find
bagels.
an actual
Sorry.
velocity. I would have to find the hypotenuse.
Because you're doing math right.
I've been to a few bagels. I've never been to where we're like, man, that bagel is significantly better than another bagel.
Providing more information.
I'll give it a try at some point. Bagels to me are kind of like pizzas, but they're all kind of decent.
Yeah, but like when you have a good one.
Okay, I'll try it. I'll try it and see if it.
That's next time bagels on campus. I was not even.
No, that's most campus for me.
And that's the big numbers you got.
How much on this?
Yeah.
It was multiple choice.
Really?
I just want to make sure for my own brain.
built in those points for doing extra work.
Okay.
So now I'm just writing out the equations just a little bit more. In the x direction, you have m1 v1 initial x plus m2 v2 initial x equals m1 plus m2 v final x. It's the same thing we done in the last problem. And then the one down here, we have m2. Oh, I wrote this wrong. m1 v1 initial y plus m2 v2 initial y equals m1 plus m2 v final y. And then you just plug the numbers in and do it, which maybe sounds trivial, like I'm trivializing it, but this is the physics done. Now we just plug in numbers. M1 is 0.9. My V initial X, I'm just taking the numbers from up top, 22.94 was 0.325 times 7 equals 0.9 plus 0.325 times V final X. And if you solve that, you get the 18.7. It's a little...
90 kilos? That's a big bird. That's like an ostrich.
All right, and then you do the same thing for the y direction. 0.9 times, and this is where the mistake will happen. If you all make a mistake on this problem, it's probably because you forgot the negative sign. Like, that is going to be the mistake. Then plus 0.325 times 0. That term goes away. So this problem is to show you all that, one, how to do x and y. And it's just the same process, just do it twice. All the x's together, all the y's together. Have fun. Grand time. Okay, are we going to do the boulder one yet? Again...
Calculate the acceleration.
We're going to do this deer one first. I'm going to save the most unpleasant one for last. Again, I keep like hyping up this boulder one. It's not bad. The bad part is the math part. The physics part's easy. Physics part's easy. The math is the unpleasantness. All right. This one is the next level of complexity. You all had 2 objects in the x and y. Now we have 4 objects. Draw a picture of it. If you don't draw a picture, it's going to be hard to keep track of it all. So you got 3 deer standing on a flat rock that's on an ice-covered pond. That's just so we don't have friction. That's the reason it's on ice. A gunshot goes off and the deer scatter. Deer A runs up and to the right. Deer B runs down and to the left. Nope, up and to the left. And deer C runs down and to the right. What's the velocity of the rock on which they're standing after they run off their platform? Again, it sounds crazy, but you can solve this with momentum, which is so cool. It's cool to me. It's so cool. You just know which way they ran. You don't know one hopped off first or they all hopped off at the same time. And you can figure out the way the rock's moving.
Okay. One trip because the other big got disrupted.
It's good. We love this.
Oh, never mind. I see.
Yeah, I translated them.
No, I know. I was like,
But good. That's like, imagine if you, again, think back when you saw this at the beginning of the semester, how awful this would be. You'd be like, why? But that's fine. You look like, you can speak math. Yeah.
right. I'm like,
That's honestly a big skill to start to speak math. It's a language.
I need to know Where you get your
So lost or TJ Maxx.
We really like to
$12.
Zero.
An email. People love the bright ones. That's a recurring theme. If you ever want to get compliments on the panel, just wear something bright. Oh yeah. It's a good. It's a rule of thumb. Look at where what?
Every time I'm alright. Oh, I'm just gonna run in the store really quick. It's not moving. It's TJ Maxx. I'll be in that complex.
So it's your mom.
I got beef. No, beef and TJ Maxx.
That's great. 2 hours.
So would that just be all?
TJ Maxx are normally in a plaza full of like 8 syntax.
I like the wording.
Oh yeah, then she wants to go home to
I understand.
That's pretty good. That's
I think mine's out.
a bunch of stuff that you don't need in your house.
So why are you talking
I hate shopping. No, I do. I don't need a sign that says. I don't need 20 signs that say love is all you need. Yeah. Various vegetables on my walls. Yeah. I get it. It makes the place look more welcoming and homey. Like Spider-Man.
Sure.
Yeah. No, I get the value there.
Wouldn't it be opposite of all the velocities that we get because equal and opposites of the deer
Sure.
line, so they'd actually.
If you like averaged out all the velocities of the deer, because they have the same mass. Yeah.
But it would be in the opposite direction because the deer are
Yep. For every force is momentum is another way of equal and opposite. But yeah, you're not gonna average out their velocity. No, build the momentum equation.
I'll do it once, not 20 times.
You only do it. Well, you gotta do it twice.
I'm confused where the rock, like what the rock is doing.
What do you think it's doing?
Is it just a fourth object?
It is a fourth object.
Yeah.
Yeah.
It's bouncing off with a one.
It's going to move back. Yeah.
So you would just
So,
Mm-hmm. Yeah. Yeah, you're solving for the velocity of the rock afterwards.
but it's still.
It started still.
At the
Yes.
start, yeah.
Yes. Yes. Good. In fact, how fast are all of them moving in the beginning?
It tells you. The 15.
That's after.
Oh,
It's not separation.
that is.
Yeah.
Oh, so you're all still.
Yes.
Oh.
All right. So the picture here is key. If your picture is bad, everything else is going to go bad. Initially, I got a rock. Is my rock moving? Nah. What about the deer? I got 4 deer. I'm going to color them to make it look. There's deer 1. It's purple. There's deer 2. It's orange. And there's deer 3. It's green. What are the deer doing in the beginning? Standing. Are they moving? No. It makes this problem start really nicely for us. Nothing is moving in the beginning. My coconut-shaped object isn't moving. And nothing on it's moving. Great, that's my initial. And then my final, and this is the one that's like, it's just good practice drawing vectors and things like that. Deer A, again, we decided deer A is going to be purple. Boom. If you didn't draw these arrows, this is good practice. 15I, 5J, that's going to be more to the right and slightly up. That's the way deer I is going to go. And this is just good practice. If you didn't try actually drawing these accurately, I encourage you to do so. In fact, go ahead and do the other 2 if you haven't. I'll give you all a few moments. Practice drawing vectors. It's a skill that doesn't go away. You're going to need it for Physics 1 and Physics 2. All right. The deer 2 is something like that. Up and to the left, they cross paths. You know what's great? Do they run into each other on the rock? Who cares? You don't care what happened while they're on the rock. You only care once they hop off it, how fast they're going.
Does the rock have an initial velocity?
Is it moving in the beginning?
Well, it's on Earth. And it's in Earth.
No. Well, it's all. Then they're all moving, and then it all. Yeah. Then you would have to add that to all their velocity at the end. It's all relative. So relative to the Earth, we're going to say they're not moving. All right, great. Again, this is just good practice. You got 2 deer kind of going up. Deer 3 is kind of going down a bunch. Which one's going to win? You can't quite tell from the picture, to be honest. Which way is the rock going to move? You can take a bet. If you want, you can try to take a bet on which way the rock's going to move. I honestly don't remember the answer, and I didn't put it here. So, let's see. If I was a betting man, well, it's gonna move up. I'm looking at numbers here, to be honest. So I am doing math, and it's gonna move to the right. I think it's gonna move up to the right. That's my bet, based on the numbers. We'll see. I don't know. Doesn't matter if you have a good prediction or not. Okay, what are we solving for? So my givens are that deer A's final velocity is 15I plus 5J. Deer B's final velocity is negative 12I plus 8J. Deer C's final velocity is 1.2I minus 18J. And they're all initial velocities. Initial velocity of everything is just 0.
This is 2 numbers.
And then you got the mass of the deer, and you got the mass of the other deer, and then you got the mass of the third deer. And they're all 70 kilograms, and you got the mass of the rock as 200 kilograms. All right, what are you even solving for in this problem? We actually probably should have started there. What are we aiming for? The rock, initial or final? Final velocity of rock. Final for final, R for rock. It's nice, simple notation. Lets you know what you're doing. Step 3, how we're going to do this. Sum of momentums. I'm going to write both of them, even though there's not quite enough room. Sum of momentums initial in the x equals sum of momentums final in the x. Sum of momentums initial in the y equals sum of momentums final in the y. And then you do it. How many objects in my initial, how many objects do I have? 4. But they're all together, so we can treat it like, in the beginning, we can treat it like one big object. In the beginning, we can treat it like one big object. At the end, how many objects will I have when they scatter? 4. In the end, I'll have 4 because they all scatter. 3 deer plus 1 rock, 4 objects. In the beginning, I have 1 object. So find the momentum of your initial object with everything all together equals, add up all your momentums of all 4 objects later on.
That's separation.
That's right.
Okay.
Yeah, it's nice. It's great. Yeah, because M1 plus M2.
Yeah.
Sure, add up all the masses times 0.
Yeah.
Yep. What's that?
The rock, well, the rock is confusing me. You said that it's final would be going up into the right.
Maybe. I don't know.
Would be like
The deer are pushing off with their feet.
They
It should
are.
go the opposite direction. We're all the
Sure. Yeah. So that's what I actually did to get the answer. Is I added up all my velocities
Oh,
in the y direction and then swapped it.
okay.
So the deer's their net velocity is kind of negative. So then the rock's going to go up. And then their x velocities, if you add up them, were all negative, like adds up to be negative. And so the rock will go to the right, so up and to the right. Yeah, the initial. Yeah. And the reason, that's only because the deer all have the same mass. If they didn't all have the same mass, they'd have to weight. I mean, all you're doing is you're weighting each velocity by their mass.
the 3 masses.
That's a beautiful picture. No, you didn't need to find it.
Yeah,
If it's already in components, you don't need to. You only. That's fine. Then do it. Then you just don't use it.
So that's what I did. And then it's the final answer. And then I did the second test.
You already have that.
You already have the I's and J's. Don't use it. Why did you do it? I don't know. Because it made you feel better, I think is what you told me. No, you always care about X and Y. If I already gave you X and Y, don't read mine. Yay! I had no idea that's right. It's fine. It might be. Remember, I don't actually remember.
So 0 is
To spare you here, I mean, this is fine. Remember, we could have added all the maps.
Yeah, I didn't realize that.
That's fine though. Yeah, that's perfectly fine. Oh, and you might want to, that totally works. You did all the X's. That totally works.
that should be 0.
Yes,
Oh, don't worry.
that should be correct. I would just have to check the math. Yeah, let me check. Let me check what the answer should be. So this is the level of problem you all should be able to do for the test. This is like the difficulty level, like the max difficulty level that you should expect on a test. So if you can do this, awesome. If not, this is the goal. Where's my deer? Alright, I was wrong. It does go to the left and up. Look, I made a guess. I have to think through why my guess was wrong.
You didn't do it?
I thought I was wrong.
Oh.
Let me think through why that was. Did I do something?
Well, it's here. If you.
I don't know, but I got it right, so I'll take it.
That tracks. Okay. Yeah, you need everything to cancel out. I had the wrong one. Yeah.
I don't know. I'm happy. I don't entirely know why I got it right.
Oh, if you add up the X's, you have an extra pods. Oh, I just did bad math. If you add up all the X's, yeah. If you add up all the X's, it's a net positive. So you need a negative to cancel that out. Yeah. But that's what I get for doing things in my head. That's why I don't try to do stuff in my head normally. Like if I'm gonna do it in my head, whatever I say, I'm not gonna say with confidence.
I do it with the calculator. I still get it wrong. So you know.
Yeah, these things happen.
I'm so sad physics 2 doesn't have radio. That's the only thing I know. Is there almost a line?
Physics 2 does have waves. It's just it often gets chucked at the end and barely covered. I spent like 2 weeks on it, I think.
No, it's better than nothing.
Yeah. 2 weeks I think was so. When I taught physics 2, I covered what a wave is.
Can you talk physics 2 again?
I have no. We'll see.
Yes.
I have no idea what I'm teaching. I don't know. All right.
I'm gonna go talk to this again.
So if we just build these equations, if we build the x1, we have m1, or they're a's and b's, ma plus mb plus mc plus m rock times v initial, they're all together, equals ma times v final x a. Sure, v, yeah, that's fine. MBV final XB plus MCV final XC plus M rock V final X rock. Yeah, rock feels out of nowhere after doing ABC. Great, that's the X1. I'm going to be really lazy, and through the power of technology, I'm just going to copy and paste this and then change all my X's to Y's because I don't want to rewrite all that. The power of technology. Because it's the same one. Y. Initial X, initial Y. And you plug in numbers. And you get an answer. I will plug in the numbers as well. For fun.
Massive rock times
All right, to spare me some writing, this first term is 0. So 0 equals 70 times 15 plus 70 times negative 12 plus 70 times 1 point plus rock 200 times v final x, and then you do some math, and v final x equals all that 70 times stuff divided by 200. V final x equals what is the answer? Negative 1.47. Yay. And then, we do the same thing for this one. Ooh, what color are we going to do for that? Green it is. All right, 0 equals 70 times 5. Yeah, so this problem seems bad, but in my opinion, it's really like... Oh, did I put the wrong thing? Yeah, no, I was like, it's looking good. But no, but do call me out. If you ever think I plug in the wrong number, you all have seen me make a lot of mistakes. You all are part of my double checking. There's a reason why people sometimes get a second opinion from doctors. It's not because the first doctor is a terrible doctor. It's because people might make mistakes or different. And medical, oh gosh. If you all think physics is bad, if you become a doctor, it's so much harder. Like, this has a right, like, you are like, oh my gosh, look at all these variables. The amount of variables you have to deal with as a doctor, like the amount of measurements that you have to take, blood pressure and various levels of various things. And I don't even know what they all are. But there's a reason why you go to different doctors, because there's so many. The human body is incredibly complex. If you all think like a car engine is complex, like human body is so much worse. And you all have to deal with that if you become a doctor. You have to know all those variables and how they interact with each other and all the effectively they're like equations, but maybe not equations. This is so much easier. Like, I can do this on a napkin. There is computers that do this stuff. And eventually maybe AI will do, there's like AIs diagnosing things based on stuff and whatever. Anywho, your job's harder than mine. If you become a doctor or a vet or, oh gosh, vet, then you got to know like a bajillion different animals. Anywho, so if y'all think this is complex, what you're getting into is far more complex than this. Use that as a confidence boost. All right, take a breather, y'all. We'll reconvene in what? We'll say 9:32 when the real time is 9:32, not the clocks in this room. They're crazy. If you take the average of the two clocks, it's the correct time. It's a math problem. And we also can't change these clocks. Like if I went over and tried to change it, it's not possible. I think they're like tied into something. Yeah, it's a weird thing.
They have like a time.
Yeah, that's the time of the east part of campus, and that's the time of the west part of campus based on,
Yeah, it's off like
the sun's just acting. Alright, so the bolder one, the reason it's just elastic energy. It's just oh, so we are going to teach center math. That's actually the slide right after. I'll start doing that today. Trying to finish it a little bit. May or may not finish it because we're gonna do a lab on it Thursday. No. Oh,
So like when I
it's very sure. It built this from wood like.
I know I was
So you're gonna build the momentum equation. So you have two objects separated, then two objects in together. You're gonna build that equation. Then you're gonna build the energy equation. Two kinetic energies to begin with. Two kinetic energies to begin with. And then it gets very unpleasant because energy is squared in terms, and our
When I
unknowns
was
are.
watching it, I was like, she is so focused right now, just like, and I was like,
It's hard to
The guy
express
who was
like without when I show it. You'll see what I mean. It's a system of equation where you have two velocities. You solve for one in terms of the other. Then you plug it in, but then they're squared, and it gets very unpleasant. And we're not going to actually solve it because it's not. It is useful to set up the problem. That's a useful skill. Doing the math takes forever.
so you would use, it was the, he graduated last year, but
Momentum and energy.
okay, and then you would use the kinetic
Then you have two equations
like
with
the
two
person that sits up, okay.
because you know their initial
I don't know if he
velocities,
does it now, but I
1 and 2. You don't know their final velocities, 1 and 2. There's two objects.
Oh.
So momentum will have the two unknowns on the right. Energy will have the two unknowns on the right. And you can worry about your stuff.
That's pretty cool. Like, hey, go to softball, hear my voice. And also watch it.
Yeah, and then we'll start center mass today. And that means I think we can start fluids, which will be fun because I enjoyed learning the fluids. I never actually had any class ever teach me any fluids. Yeah, so it'll be cool. You'll get to learn fluids. Which, are you doing it? Well, there's a lot of cool stuff in fluids. Just don't have to. So it's one of those. We're also technically supposed to cover thermodynamics.
Yeah, I know that. Oh, they were.
Oh, they covered it?
I did.
Really? Oh, yeah, no, we don't have any.
Oh, okay.
Yeah, we're not going to do it in this class. 'Cause, yeah, we're technically supposed to cover waves, thermodynamics,
Like, unless
fluids, on top of all this stuff. And there's just like, yeah, I could do it and go at such a fast pace that no one understands anything that's going on. Yeah. Sure. Yeah, we can find that. No. Maybe it's not dead, right? You should never
My dad's nickname.
That's like, my parents wouldn't like go this crazy, but they'd be like,
Yeah, but you can't just
you think I want to miss
Because
that?
they're gonna
Like,
want to
I'm not trying to play that.
I don't want it.
Oh, I know. They literally act like
Well,
they're
yeah, it's
intentionally going up there and like, not.
It's a coincidence. It's how it works. This number doesn't give you. That doesn't give you. If you want to find x and y, we're going to
Well, especially when you play college.
we have to do the square root of the square. Yeah. If you want the
That's
total
what I'm saying, like the coaches and like
together,
yelling.
total together, so you then both of those. If you're going 5 to the right and you're going 6 down, you're going more than both of those.
They had to put up with so much where they are. Like, especially since they're good in school.
Yeah.
For that, like,
They're well, they'll end up actually going.
like I think my dad, like, he down. Like,
Their final
but like
velocity.
I knew that that would never happen. Like, one, I wasn't good enough, and two, I just didn't get enough. Like, I like
So yeah, that's the key here is remembering when it comes to vectors.
Like, I love practice.
Never.
I can practice all day. You stick me in a game, I'll play
It's
this.
so.
I
It's apples and
because
oranges.
like everybody's just so like agitated all the time. I'm like, calm down. Like it's not like
Well, like, you only did it because
They do like, oh, I thought
Very
it was very
much.
much. Like, no. I mean, I feel like learning but like in game. Yeah, in the middle of it. Oh, maybe I
It was
should
also like it's funny because I used to talk to one of my friends that I used to play in high school, and it was like I was not good. He was just like, Chicago, and I was really bad. They're like, like non-dangerous. A bad environment. Like I used to. A lot of it.
All right. The boulder. Okay. The physics for this isn't bad. The physics, building the equations, we're going to build the equations, and then I'm going to show you why the math is unpleasant, and then we're not going to do the math. Okay? So, a boy sleds down a hill and onto a lake. And once he gets to the lake, he's going horizontally 10 meters per second. In the middle of the lake is a 1,000-kilogram boulder. When the sled crashes into the boulder, he bounces back from the boulder. It's an elastic collision. That's an important phrase. If the boy's mass is 40 kilogram and the sled's mass is 2.5 kilogram, what's the speed of the sled and the boulder after the collision? We assume the boy stays in the sled, to clarify, like they're stuck together. So you got a boy and a sled, hit a boulder, then they bounce off it. Draw a picture of this. And to clarify, remember they hit each other on a flat surface. And we're going to do a lab on Thursday with elastic collisions. So, yeah. Mhm.
It's further up.
Yeah, I moved things around. It'll be further up.
Are we covering the center of mass?
We are going to cover center mass, so we'll start kind of dabbling in that today. And then I'll leave a little bit maybe for Thursday. And then Thursday we're going to start fluids. And that's the last thing I need to cover before the test. So we have we're a little bit ahead schedule.
Does that mean we have a test?
Means Thursday, if we finish early, I'll probably just solve. Well, we'll technically have the lab still. Yeah, depending on how Tuesday goes, we might start the class with the lab or something. Normally we do the lab in the second half of class.
Do we do one lab drop that's not that first one? Or is that
Yeah, that first one didn't matter at all because any grade from the first reading class I don't include because people are ad dropping and all that nonsense. So your first lab isn't actually factored in, but you get one free lab drop. Yeah.
So when he's propelled backwards, is he pull off his sled?
No, he's still attached to the sled. Yeah.
Okay.
Yes. His velocity is once he's on the lake going horizontal. That's very important.
So then
How did he get to going this fast? It's just some context. Yeah. Yeah. It's just to give you context for why he's moving. So you got the boy on his sled, cruising. V1 initial is 10 meters per second. And then a boulder. There's my boulder. Is my boulder moving to begin with? No. Great. He hits the boulder. Do they get stuck together or do they bounce off each other? They bounce off each other. So the boy's going to be going backwards. How fast? I have no idea. V1 final equals question mark in the boulder. Is the boulder going to be moving? Yeah. Sure, it's a big boulder, but we're on ice. There's no friction. If there's no friction, you hit something, it will start moving, even if it's really slow. Yeah.
Do we have to break the 10 down to the next one?
This 10, it's perfectly horizontal. This is his velocity. once he is on the lake.
Oh.
Yeah. The hill is just mentioned to say, how did he get going fast in the first place? He went down a hill. Great. Go ahead, y'all. Go through the, motions given, missing. What are we solving for? And then build the momentum equations. Well, equation, because there's only in the x direction here. And I want you all to spot the challenge.
As it is, we the fact that on one side of the equation, just the point on the hill, on the other side of the equation, it's not only boxy or
I'm sure that's solved.
Wow, I was so.
Can we solve one equation? There's another equation we're going to need to bring in. Yeah, that's the purpose of this problem, is to, it's still possible to solve. Yeah. The boy stays on the sled. That's it. He stays on the sled somehow, some way after running into a boulder. And if you run into a boulder, you're probably not going to bounce off it, really. But whatever. It's about 20 miles per hour. Yeah. And the sled might have taken the most of it. He was wearing a helmet. He's fine. You don't actually put the positive or negative. Yeah, you don't need to know which way it's going. You just leave it as is and let the math. Yeah. All right, we got two unknowns, and then we're gonna, do the thing. Momentum's initial equals momentum's final. How many objects do I have to begin with? Two. And we're only gonna look in the x because of the y direction. So we have the mass of the boulder. We're just gonna call it 1 times v1 initial plus the mass of the boulder times v2 initial equals. How many objects do we have at the end? 2. We also have 2. So we have m1 v1 final plus m2 times v2 final. We're spared a little bit. The second term goes to the velocity of the boulder initial is 0. So v1 initial is 10, v2 initial. The boulder's not moving. Okay. Do you all spot the problem? Can we solve this?
No.
Why?
Because we can't isolate.
Yeah, let me just I'm going to plug in numbers and then I'm going to erase it. I'm going to plug in numbers only so that I can erase them right after. I want you all to see the problem. We have one equation with 2 unknowns. It's impossible to solve. That does not mean this problem is impossible to solve. It means there's something extra we have to do.
If it's an elastic collision, why can't we say the velocity is the same but just negative?
That'd be inelastic.
Yeah, no, it's a good question. The question was, why can't we say the velocity is the same but negative? That's only true if they have the same mass. Yeah, it just ends up being that if two things run into each other, their velocities won't be the same. I mean, you know this. Like the boulder, what's going to be going... If you run into a boulder, are you going to make it move that much? No. Yeah, so the forces will be the same, but the accelerations will be different. And yeah, it's a good question. All right. I want you all to peruse through the slides for elastic collisions and see if you all can identify when you have an elastic collision, there is something else that's relevant. There's another equation we can pull in. So spend some time, see if y'all can figure out what it is. Something else, something is special about elastic collisions. Peruse through the slides, find the slide that says elastic collisions. See if you can find what's special about it. Give you all like 20 more seconds.
That's pretty fire.
Fire is
All right, so if I scroll, boop, 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 boop. Ta-da! In elastic collisions, energy is conserved. Which means not only do we get to make a conservation of momentum equation, we get to make a conservation of energy equation. It's good practice for us.
Is this on the exam?
This problem, so I won't ask a problem that's involved mathematically, but it is important to know that energy is conserved in an elastic collision. Yeah, so there might be something like that. All right, so I'm just going to write the general form of conservation of energy. And then you all need to try to build it. And it's go through the checklist. What energies do I start with? What energies do I end with? So you all got to build this. Add up all the energies you start with and set it equal to all the energies you end with. The only thing I'm going to mention to you all is there's no work being done. There's no external forces involved, so we don't have to worry about work. If you're like, where did work go? There's no work being done here. There's no friction or applied force or stuff like that. So what energies do I start with? What energies do I end with? Go through the checklist. There's only 3 types of energy as I've taught you. Kinetic, potential due to gravity, potential due to spring.
Should be a spring somewhere. I don't know that.
That kind of happens in the middle.
What's the spring constant of Flash?
What?
Because he's smacking it on the spring. That's how it bounces.
Oh,
That's what makes it
The
an
board.
elastic.
sure.
What's his spring constant?
Sure. Doesn't matter. It's in the middle. Remember, you only care about the beginning and the end. You don't care why.
It cancels out.
You don't. Yeah. In the middle, stuff happens. Sure, who cares? We don't care. All you see is you opened your eyes, you saw them running towards each other, you closed them, you opened them later, and they bounced off each other. Who cares what happened at the end? Not us.
I keep forgetting the 1/2.
Or do you want y equals 0?
1,000.
Make a decision. Where do you want y equals 0?
Kinetic energy.
In the middle?
And then you just add the masses.
So you could, do you know where that is? No, you don't. No, and we don't actually reference that in this problem. The ground is 0.
So that's how you would find
Great.
the
Where does he start? Above or below that, or after? He did. We only use that to find the only reason that's mentioned is to say, hey, he goes down the hill at the bottom of 10 years.
So you take potential and kinetic.
If we, so we're not actually worried about up on this side. We're not worried about that part. We're only worried about you would only care about the hill stuff if I said how fast you go. How you ready to solve this system of equation? So we're trying to build energy conservation for the same situation in this short time. What energies do I have here? All of them together. All of them together. All right, so something different here is we're finding the energies of everything together, the entire system, all the objects. So, anytime we do an energy problem, we draw a picture, and we have to decide where y equals 0. Where do y'all want y equals 0 to be on my picture? The floor, which they stay on the floor the entire time. That's where y equals 0. That's always something you got to decide. You always need to decide where y equals 0 because you all have to make a judgment call on whether you have potential energy or not. So you need to know where 0 is to be able to make that decision. So, let's go through it. Do you have potential energy? Are you above or below that 0 in the beginning? No. Are any of my objects above or below that 0? No. What about the end? Are they above or below it at the end? No. Great. In the beginning, do I have stuff that's moving? Yeah, what's moving?
The boy.
So we have 1/2 M1 V1 initial squared. We have kinetic energy due to the boy. Does the boulder have any kinetic energy to begin with? No. Great. Is there any springs involved in the beginning? That's our checklist. Are they moving? Are they above or below 0? Are there any springs? Great. Initials done. Final. Is there anything that's moving? Yeah, what's moving? The boy. So he's got some kinetic energy. M1V final squared. Is there anything else that's moving? The boulder. So we have some more kinetic energy. Great. Is there any potential energy? Did they go up or down at all? No, they're still at 0. Is there any springs? No. We did it. We built 2 equations. So, I'm going to copy this over. Again, we are not actually going to solve this problem mathematically because you can if you want to. I just want to show you all how you would do it. Why am I going to give you this problem? I need you all to know that in elastic collision, energy is conserved and momentum is conserved. And I need you to be able to build those equations. That's what I need you to be able to do. Okay? That's the skill. So, chuck this over here. I'm going to go ahead and erase this number stuff. And I'm going to rewrite this top one without the term that's 0. Okay. Here's what's unpleasant. I'm solving for these 2 variables. This is a system of equations. How would you do this? Again, I'm not going to work through this whole thing, but I'm just going to quickly show you all the next step, and then we'll call it good. How do you solve for it? Well, first, I'm going to get V1F by itself. So M1 V1F equals M1 V1 initial minus M2 V2 final. I just moved things around. All I did was move things around. Here, let me write it slightly differently because I want to make it as easy to see this as possible. M1 V1 initial minus M2 V2 final equals M1 V1 final. All I did was I moved this to this side. I just subtracted it over. Nothing crazy. Great. Now, M1 V1 initial minus M2 V2 final divided by M1 equals V1 final. All I did here was I took this mass and I divided it to the other side. Okay? Yeah, nothing crazy. Now here's where the unpleasantness emerges. Now what you would do to solve this problem is you would take this whole thing and you put it in here. And then you get to square it. And do math and stuff like that. It's a system of equations. You all have the math skills to be able to do this. It would just be a little bit of a tedious process. The math here is not crazy. It's not calculus. It's not like skills you haven't done. It's just tedious. Whatever. If you did it, you get those answers. Again, I'm not going to ask a question like this on a test. I am not going to ask you all to go through this much math on a test because it has little additional value. I'm not testing your math skills. I'm testing your physics skills. What I might ask you to do, though, is I might ask you, which of the following is the correct conservation of energy equation for this problem? And then, I'd give a bunch of crazy options with variables. I say crazy. I give you options with, these variables. Can you build the equation? That's the skill I need you to know. Can you all build conservation momentum? Can you build conservation of energy? That's the skills I need you all to have. Okay? So, great. So much fun. Something I do want to point out, if you're interested in this, maybe 10 to 20% of you are. I don't know. If you do have elastic collision, it does simplify really interestingly, where if you add up the velocity initial of object 1 and the velocity of object 1 final, it equals velocity 2 initial, velocity 2 final. The proof for this, like there's a video for it, whatever. It's just kind of interesting. If you have two objects that bounce off each other, if you add up the velocities for object 1, the initial and final, it equals the velocities of object 2, initial and final. You do not need to know this. It's just kind of a cool little thing that happens. Great. Okay. So that's it momentum-wise. Yay! I'm going to start center mass. I'm not going to spend a bunch of time. We will finish early. Like, I'm not going to finish all center mass. But we're going to start it because the reason I want to start it instead of, well, one, we're like super early. But two, remember, if I can get you all something in your brain will process it in the background. And then when we see it again Thursday, it'll be easier to digest. The equations for center of mass are going to look unpleasant. Like I say, you'll see what I mean. But it's not terrible. It's not terrible. All right, great. Just don't forget about this, whatever. Okay. Center mass. Center mass is super, it's very relevant to your day-to-day life. It's something that you interact with all the time. And this example is one of those. If I had the following triangular shaped roof with a uniform density, approximately where would I place a single vertical beam to support it so that it's stable? Would you place it at point A, point B, point C, or point D? This question exists to show you why center of mass is important. Think of those children blocks you might have played with as a kid. Not a trick question. I'm just trying to activate your prior knowledge, your life experiences.
I was going to watch your story.
Because I had to but he bounced I want this. It's more like
That's true. You need someone to do X. I'll tell you what. After physics 2 is over.
Oh, it was so good.
All right, give y'all like 10 more seconds. All right, in 5, 4, 3, 2, 1. All right. So, let's see what you all put as the answers. The answer is great. It's one most of y'all thought. It's B. The answer is B. This is, for now, I haven't taught you anything. It's just like, if you want to balance it, why is it B? It's because there's a bunch more mass over here. And so like you need to cancel out kind of the force of gravity. Imagine if I put the pivot point here. I got more mass over here. Why does that matter? If there's more mass, there's going to be a force of gravity on this side and a force of gravity on this side. And the one on the left's going to win. Like if there's more mass there, the force of gravity is bigger. It's going to pull it down. Yay. So, look, you all have like played around with things. If you put something there, it's going to be nice and stable. It's going to all balance it out. When it comes to center mass, so the skill I'm going to teach you all, the thing that's kind of cool, we won't do one like this because you need calculus. So we're not going to do one like this. But what you can do with this object is if you do center mass, you can basically imagine I took this object and I smushed it to a single point. The center mass is going to be right there. And we can treat this problem, instead of like a triangle, we could treat this problem like a little tiny dot that's located right there. And we just where would you put a pillar to balance at? If you have the center mass there and I put it here, it's not going to hold up that dot. So where should I put a pillar to hold up that dot? There. You can basically pretend like that entire object is shrunk to that single dot. It's a really cool thing with center mass. Every center mass is like the center, this is going to sound crazy, of the mass. The center of all the mass is the center mass. Wild, right? What a crazy idea. Every single object has a center mass. Every single object. You have a center mass, the chair does. If something has mass, there's a center of that mass. So there's some really, really cool consequences of this. Let me actually make a new question. If I lean forwards, what happens to my center of mass? Does it shift backwards? Does it shift forwards? Does it not move? And those are the only three options. If I lean forwards, what happens to my center of mass? You can draw a picture of this if you want.
Maybe this goes for. Am I seeing this equation or
No, what happens?
Doesn't matter. Doesn't matter. Assuming the rest of your body, if you lean forward, so the only part of your body that's affected is above your waist. The only part of your body that should be changing is above your waist.
They stick you up against the wall and you have to lean forward.
Oh yeah, you all can do it. You know what? That's a great exercise. We should totally do that.
We have an hour.
Yeah, we're gonna totally do that right after this. There's not that many of us in here.
Oh, dang.
Up against the wall and you try to lean forward.
No, it's such a good demo.
Figure out why you fall face first. Because you can't counter.
Yeah, so what a great point. I love that. And we have enough wall space and a few amount of people. All right, I'll give you all 5 more seconds on this. 1. Well, I'll count down. 5, 4, 3, 2, 1. All right. So, here's you. Whatever, I'll draw it as a person. There you are, in all your sticky goodness. Never looked better. And then you're going to lean forward. All right. Where is your center of mass roughly located on your body? You all had to guess. Like, if you had to imagine, like, the center of your mass. You know, somewhere, like, in your tummy area, right? Great. If you lean forward, where's the center of that mass? What's going to be really weird, your center of mass doesn't actually have to be on your body. A good example of this is like a boomerang. So like if I drew a boomerang real quick, a boomerang, the center of mass. Ooh, these are all terrible. The center of mass of the boomerang, if it's like the center of it, it's not on the object. That's fine. Okay, great. Center of mass is forward. And someone had the really great idea. I want you all to experience. So, that it's not on your body?
Yeah, because it's like the center of all your mass.
Sure. It's because some of your mass is like down here and some of your mass is here. So it's going to be in between the two kind of blobs. And in between those blobs isn't actually on the body.
Imagine a hula hoop. The center of mass is in the middle.
Yeah, that's
somewhere in the hoop.
Yeah, that's a great example. If you had a hula, yeah, that's a great example. Hula hoop's even better than my boomerang awfulness. If you all had a hula hoop, the center of mass is in the center of it, which is not on the object. All right. So someone in the class had a really, really great idea. I want you all to experience this. Go ahead and stand up against the wall as straight as you can. Lean forward and see what happens. Try not to fall. Try it out. And I was like, I'll do it with... You gotta be straight up against the wall. It's absolutely critical. There's a reason we're using the wall. And I want you all to lean forward even just the tiniest amount and try not to fall. Like, just lean forward just a tiny amount. Yeah, lean forward. Yeah, bend at the hips, lean yourself forward and see what happens. Make sure your butt's up against the wall. Your butt cannot lean. Make sure your feet and legs are flashed up against the wall. And lean forward and see what starts to happen. Your legs need to be straight up and down. You cannot have your legs away from the wall. Your heels need to be against the wall. How's it going? Did it work? See how far you can leave before you start to fall? Eventually, you should find it like, I don't know. For me, I think if I leave a tiny bit, like, even if it's just a tiny bit, you start to fall. Yeah. As you all are leaning forward, your center mass is shifting forward. All right, so this is a really, really fun thing to kind of show. Here's the problem. If your center mass shifted forward. Remember what I told you all? We can pretend like your entire body is at that spot, and that gravity is pulling, like, we can pretend like the force of gravity is right here. What's going to happen in this situation? If you're pulling something down there, is there anything below it to stop it from falling? If you all look at this picture, there's nothing below it to stop it. There's no legs below that center mass. You fall. Just like this last problem. If the center mass is over here at this red dot and I put a pillar here, if I pull down on this, is there anything to stop it? No. So, on your body, what stops you from falling? It sounds stupid, but like what part of your body is keeping you all from falling to the ground right now?
Your feet.
Your legs, your feet. If those are behind or in front of your center mass, you will fall. And so, something I want to just mention to you all, when you all stand, there's a reason I had you all stand up against a wall. Without realizing it, when you all lean forward in your life, you do something. You stick your butt backwards. If you lean forward, you might not realize this. Let me draw the picture of this. When you all lean forward in the real world, let me try to draw this. When you lean forward in the real world, that's really good. Why do you stick your butt backwards? Because if your body moves forward, you stick your butt backwards to cancel it out. If your center of mass isn't above your feet, you will fall. If your center of mass is not above your feet, you will fall. There's another thing you all do. If you lean forward a lot, what's another thing you all do to keep yourself from falling? You kick your leg backwards. Why do you kick your leg backwards? You're putting a bunch of mass behind you to cancel out you leaning forwards. So you move your mass forwards, you move some mass backwards. They cancel out. So the other thing you all can do, if you are standing up and you want to lean forward, you kick your leg backward to keep your center mass above your leg. So this is why center mass is useful.
I really like your drawing.
Thank you. It's beautiful, right? It's like, it's got to extend the leg. Say it. What's the
That.
Oh, thank you.
Dancing.
Oh, nice. I'm learning things. So this is why we're going to calculate center mass. Center mass is one of those things that you need to put your support below the center of mass. If your center mass shifts above if your center mass is in front of your feet or behind your feet, you will fall. Someone also made the great mention of like, you all seen the Michael Jackson thing where he does the lean forward? Yeah, there's like other stuff going on there that's not, I don't remember exactly how he does it.
It's a nail in the floor.
He's really
Okay, yeah. You can only keep yourself forward if you have something to like hold. Your feet have to have something to grab onto. You all can, the Michael Jackson lean is not possible without some like, he had something that his toes were like pulling up on the floor. You all can try it for yourself. Literally try to lean forward without falling. It's impossible. If your center of mass is not above the structural part that keeps you off the ground, you will fall. The object will fall unless that object is bolted to the ground. Unless there's some other forces involved. Your feet are not bolted to the floor. Friction is never going to keep you down. Friction only left, right, and all that jazz. All right. Okay, I'm about to show you all the equation. It's going to look maybe not the most pleasant. But here, before I even show you all the equation, I'm going to show you all an example. Have you all ever calculated your GPA based on credits and things like that?
Yeah.
Center mass is doing the exact... Is that a balloon? Oh, you're fine. It's like sound like a balloon. If you all can do your GPA based on credit hours, then you can do center mass. Well, if you can't, that's fine. I'm going to teach you how. All right. Actually, you know what? Let's just do this. I'm going to teach you how to do this. I'm going to teach you how to calculate your GPA based on credit hours. And then I'm going to show you all the equation for center mass, and they're the same equation. All right. What would be the following? What would be your GPA? Your total GPA given the following scores and credits. So there's 3 classes. In physics, you got a 4.0 and it was a 4 credit hour class. History is a 3.0 and it's a 3 credit hour class. In underwater basket weaving, you got a 2.0 and it's a 5 credit hour class. Very challenging. A lot of time required. You can't make baskets without spending a lot of time. So, what we first need to do is we need to figure out, you got to scale your GPA per credit hour. So each credit hour matters. So what we're going to do is if you had a 4 in physics for your GPA, you're going to multiply that. You're going to add up all your GPAs times the credits. That's our first thing we're going to do. A 4.0 in physics, we want to scale that per credit hour. Each credit hour gets a 4.0. So like 4 times 4 plus, what's my GPA in history? 3. And that gets applied to 3 credit hours. So each one gets applied to that many hours. And then you do the last term. In underwater basket weaving, you got a 2.0 and that applies to 5 credits. So we multiply that by the 5 to kind of like make sure each one's getting evaluated for the right amount. Great. So we're kind of scaling, we're weighting each of these GPAs based on credits. Credits is kind of our weighting term. More credits means this GPA is going to affect your overall GPA more. A 4 credit hour class is going to affect your GPA more than a 2 credit hour class. That's what we're doing here. Now, go ahead and calculate this. Eventually, I'll open up the top hat one. If you all calculate this, I'll give you all a few moments. You tell me what we're going to get.
It was actually above. Yes.
Yeah. So that's
Yes?
it. Yeah.
Okay.
Yeah, because then you need to scale it back down to like.
Okay.
So we have kind of our overall GPA weighted by credit, like, and then we're going to scale it down based on credits. All right. So what number did y'all get?
B.
Well, what's this number at the top? 35. Is your GPA a 35?
Yeah.
No, that's nonsense. That's your GPA for 12 credits. That's your GPA across 12 credits. And it's not that your GPA goes up based on how many credits you take. So we need to scale it by credits. We need to figure out your GPA for like effectively like a 1 credit kind of thing. So what are we going to divide this by? If you take more credits, this number goes up. So we need to scale it by that. So we're going to divide this by something. What are we going to divide it by? We're going to divide it by the number of credits. How many credits you took? You add up all your credits. So divided by how many credits? 4 plus 3 plus 5. And what we've done is we've weighted each of our credits by GPA. And then we've divided by the total credits to kind of get rid of that. And you do that, and this is how your GPA is calculated. If you didn't know that, this is how it works. It's called a weighted average. It's your average GPA per credit hour kind of thing. And literally the math we just did is how you do center mass. When I show you the equation, you're going to be like, what? And it's literally this. Just replace GPA with distance and replace credits with mass. So, I'm going to open this up. I hope everyone can get the right answer. We'll find out. Everything's there for you. It's just, 35 divided by 12. And then, I'll show you all the equation for center mass. I'll show you all a video about center mass, and that'll be it. Oh, with center mass, also there's going to be an x component and a y component. Oh. It's fine. We have to work in vectors because position is vectors and stuff like that. All right, give you all 10 more seconds. All right, 5, 4, 3, 2, 1. So you all can almost think of this as like a center of credits. Sounds stupid, but like each credit, there's assigned a certain value for the GPA. We weighted it by GPA, then we divided by the total. And we find that per credit, your kind of center of credit kind of thing is 2.92. Great. Okay. So this slide is going to have this. All right, a lot of things. Here, before I even jump to this, so all you all did here was you did sum of GPA times credits divided by credits. When I jump to the next slide, I just want you all to see this connection, and I'm going to put it here because the next slide has a lot, and it might seem overwhelming. All we're going to do for center mass is we're going to instead sum up location. Let's call it X. We're going to multiply that by mass. And then we're just going to divide by mass. It's the same thing. Replace GPA with location. Replace credits with mass. And that's how we're going to do this. That's center mass. That's the center mass equation right there. It's called a weighted average is what you're doing here. Weighted averages are used for lots of things. What kind of things? I don't know off the top of my head, but I'll Google it in a second. Or Peter and Sophia can look it up. Look up some uses. Do you mind looking up some uses for weighted average? GPA is one of them. Center mass is another one. So here's the equation. And I'm actually going to replace this with like X. The R is better. Here, I'll write it 2 different ways. Doop, doop. If you all want the X center mass, you're going to do 1 over sum up X times M divided by sum of M. If you want the Y center mass, you're going to do sum of Y times M. So if you have a bunch of objects and you want to find the center mass of them, you just multiply where each object's located times its mass, add all of those, and then you just divide by all the mass. Just like you all did with your GPA stuff. I only have 2 problems on this, and I'm gonna actually do both of them with you all next class. There's still good ones for you to practice on your own. One of them is finding the center of the mass of the Earth and the Moon. The Earth-Moon system has a center mass, and something really interesting is it's both whenever you have objects in space, they orbit about the center mass of all the objects. So the Moon is not orbiting about the center of the Earth. And the Earth is they're actually orbiting a point that's like inside the Earth, and it's kind of funky. If you have 2 big stars, that's the other case. Stars orbit the center mass of the 2 stars. If you have 2 stars orbiting each other. Yeah, it's kind of there's a lot of cool consequences on this. Did y'all find any weighted?
It comes up in finance. It comes up in a lot of statistics stuff. Like, for example, if you have a bunch of averages of subgroups, you can back out the average of the whole group.
Finances. I don't know. I'd have to think about what. Yeah.
Another one that was interesting was evaluating employee performance.
Oh.
Based on like satisfactory levels, like performance.
Okay. So evaluating performance levels. Yeah, so if you have a measure, maybe you have a certain number of hours they work or something like that. Anywho. All right. Last thing I want to show you all. So I keep telling you the center mass is useful. One of it's for like balance. Another one of it's for like orbits. Another one of it's, well, center mass doesn't do GPA. Another one here, it's a cool YouTube video. And this is going to be kind of funky because I'm streaming and I'm going to play a YouTube video. And this seems to just be yay. Okay. So this is a cool little video to show you if it works. Another reason for center mass. So they're going to toss some objects that are complex, like a tennis racket. And they're going to do like a bunch of flips and things. If it loads. Ooh. Yay. All right. All right, so first they're going to toss an object. And this is the last thing we're doing. It's just a minute video. And it's going to look really complicated. Like, look how complicated. It's like spinning and man, wow, look at that complex. Man, that'd be so difficult to figure out. If I said find the position, and there's another crazy kind of object. If I said find the position of this object at some time, like, look how complicated this is. It's like spinning. And if I said find the location of the top of the tennis racket at some time, it's going to do some like crazy wiggly waggly thing. But when you look at, so now what they've done is they've painted a dot at the center of mass on these objects. So the tennis racket, they found the center of mass and they painted a bright dot on it. And they did it for every object. And so something that's really interesting about this now, so it's the same crazy object. And when they toss it, when you just look at the center of mass, it just follows a parabola just like you'd expect. You can pretend like the whole object is concentrated at that point, and the object just does what you expect a ball to do at that point. These are the same crazy objects. You all can't see the crazy object, but trust me that it is. The center of mass, you can pretend like the whole object is just squished to that dot. And then it does exactly what you all expect things to do. So that one's not at the center of mass. Now this one is at the center of mass. And it just makes a nice, like what you all expect. So center of mass lets us take a really complex object and turn it into a single dot. A single dot is so much easier than a complex object. So again, I'm just trying to sell you all on center of mass and why it's so useful. Last video of it, whee, look at it go. It just looks like a parabola, just like projectile motion. Why is this so useful? Every single projectile problem I've given you all, you haven't cared the shape of the object. Why? Because you were solving the trajectory of the center of mass of the object, which is kind of nifty. So, anyway, there you go. That's it. Next class, we'll do some math and things. We'll actually do a couple problems, and then we'll start fluids. And fluids is going to be super fun. Yeah. Fluids has so much cool, fun stuff in it. Hey, have a good one.
I emailed you, but I won't be in class on Thursday.
Sure.